Alright guys, this is part 2 of the video on testing conservativeness of a vector field using the gradient. So, I'm going to give another physics example for this case. But before that, let me talk a little bit about magnets in physics. So here's our magnet, here's our north pole, and here's our south pole. In elementary school, you've learned that when you put magnets together, the north and south poles attract each other, while the north pole and a north pole, or a south pole with a south pole, will repel each other. So, again, how do we express this using vector fields, similar to electrical charges? In this case, by convention, we're going to draw a line from the north to the south pole, and we're going to let these little arrows point from the north pole and point back into the south pole. And here's another field line here. There's actually many field lines, but I'm just drawing 2 of them for simplicity. So, you've probably seen the experiment here where if they point a magnet into a loop of wire, it's actually going to generate an electrical current. And you're going to have a little meter, in this case either a voltmeter or an ammeter, that twitches when you insert the magnet into the coil of wire. Now, that's actually going to be the example I'm going to do right here. So let me just erase and clarify this. Pretend that we have a loop of conducting wire. So, this means that electrons can flow freely through the wire. And now, let me put a magnet through it. So, as I insert the magnet into the loop of wire, what's going to happen is there's going to be a current through the loop. But why? What happens actually is there is going to be an electrical field again. But this time, it's going to look a little different from our last example. It's going to point like this. And so, in this case, it is the electrical field that is actually pushing the electrons in the wire, let's say right here, to start moving. And so, if the electrons and the electric field are moving in a counterclockwise pattern. In this case, because a magnet is generating this electrical field, there is a measure of rotation of the electrical field. So the curl of the electrical field is not zero. That means the electrical field is non-conservative. As you can see here, if we use curl and the vectors are pointing this way, it's going to curl around the center of this. And now, if we go back to our previous example, where we tested f using the divergence of this, using the gradient function and the vector field f, we know our electrical field is non-conservative. And we know that we can only find our little f right here if f is conservative. But let's try to see if we can make it work if E is non-conservative. So, what I'm going to do is I'm going to try to substitute E into here, and I'm going to try to find a little f. That is our potential function. In this case, E is non-conservative. So, if we plot our function again, and here's our rotating vector field, just like this example. It's located only on the xy axis. We know that when we take the gradient of a scalar function, the arrows are going to be pointed toward a local maximum. So in this case, let's start with this arrow. We see that it's going to it's pointing toward a local maximum. So in this case, let me just draw a function, a 3D function, into the z-plane based on this arrow. So this function is starting right here from the center, and it's going to increase. It's going to increase based on this arrow here, because remember, when we take the gradient of this scalar function, our vector field f is going to point toward the direction of the local maximum. So in this case, because it points toward here, our 3D function is going to start to go upward like this. Let's go toward this arrow. It's going to increase. It's going to increase and increase. When we get to here, it's going to loop back on itself. It's going to increase and increase and increase. And here's our function. We just draw the lines just for height purposes. But at this point, we have a problem. When we get back to the original place where we started, this line overlaps this line. But remember, for a function, that's not possible. A function, if you give it an x and y value, let's say right here, it can only have one possible output on the z-axis. You can't have two possible values just based on one x and one y value. So this actually violates the definition of a math function here. And so our little function f doesn't exist here. So unfortunately, it's not possible to have a Matterhorn-like function for this case. And so this is not possible. And so in this case, we tried to assume, we knew that E was non-conservative, and we tried to find a little function, f, anyway, but it didn't work out. Because when you have a rotation here, it's going to loop back on itself in the direction of the local maximum. But you can't have a function that has two outputs, or even more. And that's it for the video, guys. I hope you find this intuition helpful, and hopefully it helps you to understand why this works.